Hi, everyone. So thank you for coming to this class. I'm substituting um, Dr. Kim Sang, who is sadly unwell today. I think we're taking it in turns. So I'm just going to deliver his class on his behalf in this 3-hour Zoom session. And let's give it another minute, and then I will begin. Okay? Thank you. And sorry for the slight delay in starting the meeting. I had to get everything working. Also, I apologize if I am working from the office, which means my setup is slightly less than ideal for Zoom teaching. Try my best, and of course the TV is already not working properly. However, I will do my best to keep everything monitored as much as we can. Okay, Dr. Kim Sang is also very good. Okay, just give it another minute for people to join properly. Good morning, everyone. Yeah, so sorry. By the way, because I have to do things with just one screen, please do let me know if there's any issues with with what you can see. Okay, so if I'm gonna try as usual. I'm still organizing my things here. I'm gonna try as usual to keep the meeting chat and other news open so that I can see your questions and things like that. But just with on screen, some of the slides might be a bit obscured. So please let me know if it becomes very annoying. Luckily, I think the slides are in 4/3, so it means I can hide a little bit the side of the screen. Okay, but please, if I'm missing things, just let me know, and I will make sure you can see everything. Okay. Anyway, I think it's high time for me to start. I wasted a few minutes getting everything organized. So last week, you looked with, again, with Prof. Tan Kim Sang at oscillations, simple harmonic motions, okay? And now that's one of my favorite topics. That's what I've just been teaching at the master level in civil engineering, but you've done it with him. And today we're looking at the next follow-up on that, which is wave motion. Actually, these 3 topics that you just tackled after the test are somewhat related. We're looking really at different things, but they are somehow related to each other. First, you looked at rotational motion and things like the angular velocity, omega. Now, the angular velocity, omega, came back in oscillations, isn't it? The formula had omega t in there. Why? Well, because oscillations are not circular motions, but they can be assimilated to circular motion, okay? They can be treated mathematically similar to circular motion. Now, wave motion relates in a similar way to, and actually even more closely, to oscillation. We'll see that whilst waves are not just oscillations, oscillations have a big role to play in how waves behave. And we'll see this in the next few slides. So first of all, what we're going to do. First of all, we'll look at types of waves. So today we'll concentrate on progressive waves, which have 2 subtypes, transverse and longitudinal. Next week, you will look with Prof. Venkat at stationary waves. So the waves that you create, for example, in a musical instrument, where the strings just oscillate up and down, but don't move. Now we'll look at graphs of progressive waves, how they look at it, how they look, how we can define their properties. And we'll then look at the intensity of waves. So what's the intensity of waves? What does it mean? And how we can maybe use the intensity of waves to calculate certain properties. So for example, the power of the source of waves, okay? We'll then look at the one proper applications of this wave topic, which is polarization of transverse waves. So first of all, what's a wave? You've all seen a wave. You've all played with a rope and shaken a rope and seen these waves traveling around. You've all been to the seaside and see waves in the water. Okay? And waves really look, when you see waves in the water or when you just shake a piece of rope up and down, waves look like this graph here. Sorry, let me just select the, sorry, again, it's very uncomfortable doing this with just one screen, but I just have to live with it. Highlighter. No, my mistake. Laser pointer. Okay, so waves just look like this. Okay, so again, something goes up and down. It's got crests, it got troughs. So crest is the upper portion, troughs is the lower portion. And each wave has certain properties. They've got an amplitude, which is how much is the maximum displacement of your medium. Medium being the water, medium being the rope, medium being the material that the wave is transmitted through. Okay, what makes the wave? So the amplitude is the maximum displacement. The wavelength is simply the distance between points where the wave just repeats itself. So from one crest to the other crest, but also it should be the same from any point, from say, this point to this point, or as Dr. Tan drew here, from a random point like here to here. The wavelength is just how long in space does the wave take to repeat itself. Okay. Now each wave also then have a frequency. So they've got a space properties. So in space, how long is the wave front? How long does how distant are the points where the wave repeats itself? And then it's got time property. So how often does the wave repeat itself? What is the period of the wave? And this is in a callback to the oscillation topic. So in oscillation, you had the period of the oscillation, isn't it? How often does how long does it take for the oscillation to repeat itself? That's exactly the same thing in waves. So this point will go down, will come back up. How long does it take? We'll look at some graphs later. And of course, when you have the period, you also have the frequency, which is 1 over the period. So how often does the wave motion repeat itself in a second? Now, of course, waves move. So waves move in a certain direction. You'll see next week, even stationary waves technically move. I'll leave that for next week, but they do. So waves move. Actually, it's one of the definition of waves. They transmit energy. We'll see in a second. They've got a direction of travel. They have a speed. Again, if you've got a rope, or let's think of something more everyday. If you throw a stone in a pond, if you throw a stone in a body of water, the waves will originate where the stone hit and will travel outwards. They will have a speed. Now, that speed, we can derive it, but we can just accept it for this week, that the wave velocity, the speed of the wave, is given by this function here. V equal F lambda. So, these are really the basic properties of a wave. Okay? So, let's now move on to a bit more definition of the waves. As I said, we're looking at progressive waves, so waves that very visibly travel. Okay, so again, the definition is what's written here. The disturbance propagates carrying energy. Now note, the disturbance propagates. The particles that make up the wave don't travel along the wave. They move a bit, so we'll see transverse and longitudinal waves. The particles that make up your medium move. The particles of water in the sea move, but they don't move along with the wave. The wave carries energy without moving any specific particles along its whole path. Okay? Now, the wave, though, is made up by oscillations of particles, generally, or energy like electricity and magnetic fields, which you just need to know the electromagnetic field oscillates. We don't need to know about, we don't need to go into why it oscillates. We're not doing electromagnetism in this module, but just know that light waves, radio waves, are an oscillation of the electromagnetic field. But more physical waves, so sea waves, earthquake waves, waves in a piece of string, sound waves in air, work by moving particles. The particles oscillate. And they can oscillate perpendicular to the wave direction. If you think about it, let's see if this works, by the way. Okay, works a little bit. Sorry, it's done. In this case, the wave travels, in both cases, the wave travels in this direction. Okay, if you've got a transverse wave, which is the very everyday ones you see in the sea, the particles will travel up and down. Okay, so in this case, with a spring, which could be the same as a little rope, the particles will travel up and down, whilst the wave will travel horizontally. So that is a transverse wave. Okay. Now the other type is a longitudinal wave, also known as a compression wave, where instead the particles will travel in the same direction as the wave. Okay. So they will travel, the wave will travel still towards the right here. Okay. The particles will travel in the same direction back and forth. Okay. So that's called the longitudinal wave. Now you can simulate a longitudinal wave, of course, with not simulate. You can create one with a spring, like shown here. But the main example of this is sound waves. Also, some earthquake waves. To go back to things that engineers, like I teach in civil engineering, some things that civil engineers see. They see earthquakes. All of the civil engineers that will do the master will do earthquake loading with me in a few years' time. Okay, some of the earthquake energy is transferred with transverse waves. Some of it is transferred with this longitudinal compression wave. Now, besides the fact that the movement is along the same direction or perpendicular to the wave progression direction, the principles then are the same. The terminology is the same. You see there's a wavelength, there's going to be an amplitude, there's going to be a period, and so on and so forth. And there's going to be, of course, a wave velocity. Everything stays the same, just the direction of the particle oscillation is different in those two types. Now, one important thing, one link back also to what you did last week is what I just said about oscillation of the particle. So the wave travels, the particles oscillate. Now, an interesting thing, and it might be useful to make sense of some of the graphs you see later, is when I say oscillation of the particles, I do mean the same oscillation that you saw last week. So basically, an interesting thing is when a wave travels, the particles that make up the wave move in simple harmonic movement. Move following the oscillation rules you saw last week. So each of these particles that make up your medium move with the same rules you studied last week. Of course, they're a little bit out of phase with each other. So when this one is at the maximum, this one is not quite there yet, it's still traveling up. When this one is at the minimum, this one is still traveling down, whilst this one is traveling up again. So they're a bit out of phase with each other, but each individual particle is moving like this. So let's move on now. And now, Tan here wants to talk a little bit more about longitudinal waves because they're the slightly less intuitive ones. The transverse waves, we all have a nice image of them. We've all seen water waves. We've all been to the seaside. We've all thrown a stone in the pond. It's very easy to shake a piece of rope and see the wave traveling. Okay, I think we've all done it as a kid. Longitudinal waves, a little bit less easy to see. So again, the typical example is sound. And this is an example with a drum. And the drum is the most simple case. So when the drum membrane, but could be a drum, could be, by the way, a speaker. That's how speakers work. They've got a membrane that moves up and down, or in this case, left and right. So just imagine here, the membrane is to the right. It's compressing all the air particles, all the air molecules near the drum itself. It's creating a high pressure. Of course, this high pressure will then dissipate. And what will actually happen is this pressure front will travel. So as the drum moves to the other side, it's going to create a vacuum. Well, it's going to decrease the pressure in front of it because the particles will follow it a little bit. And again, this will create these fronts of rarefaction and high pressure. They then will travel along the air. Okay? And they will travel more or less like shown here. So the particle the displacement of the particle displacement will follow this dark line, and the pressure variation will follow this line. When the particles don't move, it means that the pressure is at the lowest. When the particle moves, it means the pressure is at the when the particles move, the pressure is when the particles don't move, the pressure is at either the minimum or the maximum. So basically the particles are standing still here and here. When the particles are moving as part of their oscillation, when the particles have the maximum displacements, then the pressure is at the minimum. We'll come back to that. This is quite, don't be surprised if you find this a little bit confusing. Do look at the graphs yourselves and try to see if you can slowly understand them. Don't worry too much if you find this confusing. You'll see the application will look at it a little bit different. But try to understand how this works. It will also relate a little bit to the general movement of waves. Okay. Now, one thing to Prof. Tan is really highlighting is, remember, this is a graph. So this displacement indicates the magnitude of the displacement left and right. It doesn't indicate the displacement up and down. In this case, the displacement is left and right. Longitudinal waves are a little bit less intuitive to see because of that. Okay. I will see if I can find an animation of this, and I'll post it on Excite for you guys to look at. Okay, I think that's going to be quite helpful. I do apologize, I didn't have much time to prepare for this, but I will try to post a link later on the Excite. Okay, so let's move on now. Now, another type of waves that, again, it's very everyday. We'll see. Hopefully, sorry if somebody's blind, but I don't think we got blind students at the moment. But even if you don't see, we're all immersed in electromagnetic waves. Electromagnetic waves, I'll just say a few words because it's really quite outside the syllabus in terms of understanding the maths behind them. But they work with oscillation of the electric and magnetic field. Basically, this oscillation travel in air like a wave, like a water wave, like a sound wave, same kind of concept. Of course, they go very fast. The speed is this 300,000 kilometers per second, which is about 300 million meters per second. So the wavelength of these electromagnetic waves are as shown here. You go from gamma rays, which have got a very low wavelength, to visible light, which has got a wavelength of this kind of order of magnitude, 10 to the minus 7 meters, to microwaves and radio waves, which have got wavelengths in the order of maybe even the kilometer. Now, the wave speed is fixed for light, for electromagnetic waves, to this number that I mentioned before. That means that if the wavelength changes, the frequency of the wave changes. So if the wavelength goes up, the frequency goes down. Do we need to know the EM spectrum for the exam? I don't think so. No, I haven't seen the exam and I'm not writing this portion. Let's move on for now. So let's now look at graphs of progressive waves. Now, this could be transverse, it could be longitudinal. It doesn't really matter. We're just looking at displacement. Okay? So you find it easier to think about them in terms of transverse waves, i.e. waves where the particles go up and down. Do that, but it's the same thing. But you see, of course, if you've got two waves, they are moving along their whole path. Sorry, not two waves. Look at two particles, okay? So each particle, sorry, my mistake, these are the graphs of particles, okay? So the wave is moving in whichever direction. Let's say the wave is moving this way, and the wave graph would look something like this, of course. And we're looking at a particle which is, say, here, that's particle A, and a particle which is, say, here. This is particle B, okay? So I can write with this a little bit. Give me just a second. Okay. So this is particle B, okay? I need to use the mouse. Particle B, let's say, moves like this, okay? Starts from the neutral position and it moves up and down. Now, particle A moves like this, let's say. Particle B moves like this, okay? So each particle follows a simple harmonic motion, okay? I'm so sorry. I do apologize about this. I didn't quite understand the slide at the very beginning. It's a good slide, but it's not mine. So this graph here is the wave, and you've got particle A and particle B. So if we plot the motion of particle A and particle B, you've got particle A going up and then back down. Particle B is doing this. So this is a plot of the wave against distance. This is a plot of a particle motion, the displacement of an individual particle versus time. Okay, so this is a snapshot of the wave in the displacement distance. So basically, you're oscillating a rope, you're taking a picture of it. Time 1, time 0, and at time 1. Okay, and delete this. This graph at the bottom here is instead a plot of the particle motions. Yeah, I'm getting to the phase of the particle motion over time. So that's particle A, and the dotted line is particle B. Now, what is phase now? Particle A and particle B are both part of the same wave, okay? But as I was mentioning before in a previous slide, they're both oscillating with the same property. They both have the same frequency of oscillation, okay? They both have the same period. However, they clearly don't have exactly the same movement. So when particle A is in the neutral position, it's at 0 displacement, it's moving up. Particle B is at a positive displacement and is moving down. Okay, so particle A is moving up, particle B is moving down like this. Now, when we've got particles that are moving in such a way, so they've got the same oscillation property, they've got the same period, okay, they've got the same amplitude, but there are different stages in their oscillation, we say that they've got a phase difference. Okay, so we say that the oscillation is the same, but there are different stages. They are out of phase with each other. So if you think about it, my hands are moving with the same periods, same amplitude, but they're going the opposite way. Meaning, when one is positive x, the other one is negative x. Okay, in case you can see my hands. This is the same with this particle. Now, how can we quantify that phase difference? Well, to quantify the phase difference, we go back to kind of an analogy. And it's just an analogy. These particles are not moving in a circle, but we can use the movement in a circle, and I'll post another video to show you how that works, to represent the oscillation. That's why we use omega, that 2 pi f, for the equations that describe oscillations, okay, that describe simple harmonic motion. We use this omega. Do you remember what omega is? It's angular velocity. So basically what we do is we define the full movement going from here, up, down again, and back here. So an entire oscillation as a rotation, a full rotation. It actually looks the same when you plot it in certain ways, okay? And if we do that, we can say that moving from here up, down, and up again is analogous. It's similar. We can represent it with a rotation, which means that we can say that the particle has gone through a rotation of an entire revolution. It's gone back to the beginning, 2 pi radians. If we can do that, then we can represent the distance between these phases, the fact that there are different stages, with an angle difference, okay? So we can say that if a particle is here, the other particle is, say, up here, they are a quarter of the revolution, a quarter of an entire circle, which means there are 90 degrees out of phase. If one is here and the other one is here, you can say they're half a revolution, so 180 degrees out of phase. In general, you can find the angle of out of phase using this formula here for the time, let's say. Let's look at the time first. So you know that the entire revolution, the entire period, we say is 2 pi. Now we also know that the period is t. So if the difference in time divided by t should be the same as the difference in angle divided by 2 pi. So the difference in angle, phase difference, is delta t divided by t times 2 pi. We can also say the same thing in terms of the path. So if a particle is here and the other particle is here, they're half a wavelength away from each other. This particle will be then going down, this particle will be going up. They're both at the neutral position. They are, again, half a wavelength, half a oscillation away from each other. We can do the same analogy. In this case, instead of using delta t and t, we can use delta x and lambda. And we can say again that the angle difference divided by 2 pi is going to be the same as the space difference divided by lambda. So again, we can find another formula. In the end, we can write this general relationship here at the bottom. Looking at the question, so we can say that the phase is the delta x between two particles, such as the horizontal distance. Yeah, we can kind of say that the phase of the two particles is what's the difference in there, where they are in their oscillation. You can define it in terms of delta x, the path difference, or in terms of delta t, the time difference. Exactly. And again, this all boils down to this analogy. And again, it's an analogy. Particles don't move in a circle, okay? They move up and down, or maybe left to right. But we can represent their movement using this kind of similarities with oscillation, with circular motion. Okay, so let's move on. So there's a simple example in terms of this phase. So this is a wave with a wavelength of 4 centimeters, and you've got 4 points, P, Q, R, and S. So particle Q, so which statement is incorrect? Particle Q has a maximum velocity. Now, remember what you did for oscillation. Is this wrong? Is A wrong? Particle Q is at the zero displacement point. Particle Q, let's say, is moving up and down. So let's say particle Q, if I can do it, is moving up and down. Okay? Now, particle Q is at the neutral position. Do you remember a property of when particles are in the neutral position in oscillation? Neutral position is zero acceleration, maximum velocity. So actually, A is not wrong. A is correct. Particle Q is moving in simple oscillation motion up and down to be part of this wave. When it's in a neutral position, it's got a maximum velocity. Now, okay, you know already the solution is B, so let me do the other one first. C, particle S is moving downwards. Well, imagine this wave is traveling in this direction, okay? So particle S is here. In the next time step, the wave will have moved a bit further this way. So where particle S will be, particle S will now be here. So particle S will have moved down. So this is actually correct. Sorry. Now the distance PS is 3 centimeters. If the entire wavelength is 4 centimeters, and this is a regular wave, then PS is quite obviously 3/4 of that. So 3/4 of 4 is 3 centimeters. So this is correct. Now, P and R are in phase. Phase means no difference, that their phase angle phi is 0. Well, P and R, P is at the top, R is at the bottom. They're definitely not in phase. P is at the maximum, R is at the minimum. They're actually 180 degrees pi out of phase. So this is definitely wrong. Okay? By the way, a good example to do is move the graph a little bit and see where it would be going. Okay. Okay. Now, let's do the next.
Okay. So if they're in the same phase, right, that means they are at the same point. So if one is at the crest, the other one must also be at the crest.
Exactly. P would be in phase with this point here. Let's call this P2. So P and P2 will be in phase. When P moves down, then P2 will also move down. Another point in phase would be Q, and let's call it Q2. These 2 points will be in phase as well. Okay? So this is just definition so far. Now let's look at one property of waves. As we said at the beginning, waves transfer energy. Okay? Wave transfer energy in space without moving the particles. Well, moving the particles a little bit, but not along with the wave. They just oscillate in place in the same position. Okay? So the energy is possessed, so each particle has got an energy which will be transferred to the next particle through whatever, chemical bonds, solid bonds, pressure waves. This energy is transferred from one particle to the other. Therefore, you can calculate the at least an analogous, at least an indication of the wave energy using the energy of the particles, okay? And you've done the energy of a particle in oscillation, in simple harmonic motion, last week, okay? The energy of the particle is given by this formula here, which is just the kinetic energy. It's half m, this is v squared. And what you did last week is the velocity magnitude is omega x, okay, times cosine omega t, but the maximum will be when cosine is 1, so the maximum velocity is omega x0, omega times the amplitude. And of course, for the total energy, for the maximum kinetic energy, which is the same as the total energy, it will be half m v squared, which is omega squared amplitude squared. Okay? And we just rewrite, because of the normal terminology of waves, we just rewrite this slightly, saying that the amplitude, instead of being x0, we just call it a, okay? We say that m omega squared is k, okay? Of course, we know that omega is 2 pi t. That's from last week, okay? So the total energy of the wave is given by this half k a squared, okay? Which means that the total energy will be given, proportional to the amplitude square. So k is a constant, okay, given by the period of the wave. The energy of the wave will be proportional to, the symbol means proportional, okay, to the amplitude square. So if the amplitude square doubles, the energy doubles. That means that what happens if the amplitude doubles? So the amplitude doubles, A doubles. If A, let's say, is if A2 is equal to 2A, then A2 square will be, of course, will be, of course, equal to 4A square. That means the energy will go up 4 times. Okay? So, and again. Okay, so the energy is proportional to the amplitude square. Now, that's interesting. Now, what we're also quite interested in is the intensity of the wave. So how much energy, if we generate a wave, how much energy will be spread over a certain area, okay? So if you're looking at the sun, if you're standing under the sun, your skin will get warmer, isn't it? You will get warmer. The ground is getting warmer because the sunlight is hitting it. How much energy is being transferred for the area of skin or for the area of the ground? That is called the intensity of the wave. It's really the rate of energy flow, the EDT. Now, what's the EDT? Energy over time is power, okay? So energy of the time is power per unit surface area. So basically, say the sun emits, I don't know, that's not the sun. Say a light bulb emits 100 watts, power of a light bulb is 100 watts, say. These are the old filament light bulbs. You might not have seen them very much. Well, not for the past 10 years, 15 years. But you are, I don't know, 10 meters away, how much energy actually hits you? What you do is you divide the power by the surface area that the power is being transmitted, and that gives you the intensity. So the intensity is the power over the area. Now we use S for area because we're already using A for amplitude, so we use S for surface. So again, the intensity, that means, is directly proportional to the energy. If the energy is higher, the dEdt will be higher, the intensity will be higher. And it's directly proportional, therefore, to the amplitude square. Now, power, of course, is dEdt and is measured in watts or joules per second. Now, what's the implication of this? So this is just the implication of this. If these are all true relationships, so if the intensity is proportional to the energy, which is proportional to the amplitude square, you can also say this. So I1 over I2. So if you're comparing two intensities, the same ratio will hold for the energies of the waves, and this ratio with the amplitude squares will hold for the amplitude. Okay? Now, if you've got a spherical wave, so what's a spherical wave? A spherical wave is a wave that originates from a point source and covers a spherical area. Examples: sound. You shout. Well, no, maybe that's not how you shout. You've got a nice omnidirectional speaker. The wave will propagate from a point, the speaker, everywhere. Okay. An even better example, a light bulb. You turn on a light bulb, the light will spread more or less as a surface around it, as a sphere around it. Okay? There's a nice picture in the next slide, I think. A typical example, a star, our sun. Our sun is essentially a point source. Of course, it's very big, but for the distances involved, it's a point source, which emits energy in all directions. So basically, it emits this, let's say, this power in the forms of waves going in all directions, and they expand. The area covered is spherical. So let me just jump in front. The area covered is this. Okay? So basically, this is your point source, and as you move away, this sphere becomes larger and larger, and the area becomes. Come back to this formula. So as the distance r increases, the surface area increases, and it increases with the square of the radius. Now, for the area of a sphere is given by the surface area of a sphere, it is given by 4 pi r square. Nothing to learn here, it's just a typical formula. I never remember it, I keep Googling it. If you need it, it will be given. I think that's the area of a sphere, 4 pi r squared. That means if you want to calculate the intensity of a spherical wave at a certain distance from the origin, you need to go power divided by surface area, so over 4 pi r squared. You've got a 100 watts light bulb. 100 watt is the power of all these electromagnetic waves being emitted from the light bulb, and these spread spherically around it. So the intensity, wherever you are, will be given by that power divided by 4 pi r squared. The intensity will be inversely proportional to the square of the radius. So it's the inverse square law. So basically, if you want to compare the same waves at different distances, the intensity will be related by this formula here. So I1 over I2 equal R2 square over R1 square. There's examples of this in the tutorial that you'll all do with either me or Stan during your tutorial this week or next. So of course, the intensity is related to the amplitude square. Therefore, the amplitude square is related to the inverse square law of the radius. So given this is square and this is square, you can actually do this relationship. That also generally means that the further away you go from the source, the amplitude of the wave will become smaller because the power per unit area, which means kind of the power that every single wave needs to carry, every single tiny wave, becomes smaller, the amplitude will decrease. That's one way of seeing it. Okay. And these are just the same formula rewritten to derive that. So again, I1 over I2 is equal to this formula. I1 is P for pi R1 square. I2 is the same with R2 square. If you do one over the other, you end up simplifying to this R2 square over R1 square. Okay. And this is a more graphical example using a power source, using a graph, using a more sketchy, using a sketch, sorry. As the point source moves, the intensity at radius r will be I, radius 2r, again, is proportional to the square of the radius, so it will be I over 4. At 3r will be I over 9, at 4r will be I over 16. Therefore, the intensity will decrease quite quickly with the square of the distance, not linearly. Now, an interesting thing is, if you've got plane waves, i.e. waves that just travel straight, say a string, shake it, and the wave travels around the string, technically should propagate forever with no change or loss of intensity. Will that happen? No, because there are other factors. So there are factors such as in a real wave, there's friction, there is energy loss due to maybe sound being created and so on and so forth. There's a lot of ways of energy for the energy being lost, but technically it should propagate forever with no change in intensity. Another question, what about a circular wave? So you throw a stone into a pond, and the water waves propagate around it. Now, in that case, you don't have a spherical surface, what you do have is a circumference. Now the circumference is 2 pi r. That means that if you got just a 2D situation, instead of the wave spreading in 3 dimensions as a sphere, it spreads in 2D like a growing circle, then the intensity will be proportional to the radius, not the radius squared. Okay, so that's just a little add-on here. So that's the intensity. So just remember, the intensity is power over surface. If I tell you this is the intensity at a certain distance and it spreads like a sphere, then you will know the intensity, you will know the radius, you can find the power. Okay, this is a typical question you might be asked. Okay, or I tell you the power, I tell you the radius, find the intensity. Or I tell you the intensity at one radius, I tell you another radius, find the new intensity. All these questions you can imagine. Look at the tutorial, we'll go through some of them. Now, the last thing we need to cover, polarization. Now, only transversal. So what's polarization really? I'm gonna move here, okay? Then I'll go back to the previous slide. Now, each wave has an inclination. You can imagine, you're shaking the rope, you can shake it vertically, you can shake it horizontally, you can shake it at an angle, okay? Now, if you imagine a lot of waves, especially light waves, okay, this is most applicable to EM light waves, but it's really just a generic idea. If you've got lots of waves, EM waves, you turn on a light bulb, all the waves will be generated, they will have probably a similar energy level, they will all oscillate in different axes. Again, as I said, you can oscillate things horizontally, vertically, diagonally. They all have the same energy, they all have the same amplitude, they all have the same period, but they've got different orientation. They are all at 90 degrees from the travel, but they have different orientation. When we say we polarize the wave, say in the wave direction, means we're trying to make all the waves go in the y direction. That means, because we cannot really rotate the waves, at least not yet, what we do is we do it in a negative way. We stop all the energy that is not in the y component, in the y direction. So it's kind of like this. So let's say you've got a vertical wave, you've got a horizontal wave. This could be even a rope. You've got a rope, you're oscillating it, okay, between here and here, and you're oscillating it going diagonally. Then you put a slit, which is vertical. The rope needs to pass through the slit. The rope fits through the slit. What the slit will do is it will stop all the horizontal components of the oscillation, because the rope will just hit the side of the slot. And only the vertical component will go through. So at the beginning, you've got a wave that is oscillating diagonally. At the end, you've got a wave that is just oscillating vertically. The energy, intensity of this wave will go down, because again, you've not taken the wave and rotated it. So if this amplitude was, say, 1, you've not taken this 1 amplitude and rotated it up. No, you've decreased it. You've stopped the horizontal component. You're only left with the vertical component. So only the y component can pass through. And generally, if there is a random distribution of wave orientation, say in a light, generally we assume that a light bulb will create a uniform distribution. The filter that polarizes it will stop half the energy. So a subsequent filter will rotate the energy further, of course, because again will reduce will again cut all the components which are not aligned with this second filter, and so on and so forth. Okay, and we'll see the formula in just a second. What's the practical effect? Well, this is a typical case. So one application of polarization is your sunglasses. Sunglasses are polarized, meaning they stop some of the light going through. They reduce the intensity of the light going through. What does it mean? That if you take sunglasses and you put one sunglass, say with orientation vertical, only light only the vertical component of the light waves will go through. And then you take the same filter and you put it horizontal, which means only the horizontal component will go through. Well, you stack them. The first filter stops everything that is not vertical. The second filter stops everything that is not horizontal. But there's no horizontal because the first filter already stopped all the horizontal. Therefore, you get black. And that's a typical effect of polarization. So let me go back to the previous slide. So generally, we polarize light with actually this idea here. We just create very thin slots, not slots you can see, slots that are so tiny that will stop the light going in one direction. Or we can do it with different physical properties, which we'll see. And Polaroids are an example of this. They're called Polaroids. So the plastic sheets that are highly strained to align plastic molecules in one direction. And this basically means that the plastic module will strongly absorb light in one plane while allowing the light going through in the other plane, okay, perpendicular to the previous one. And therefore, we can say that all the light going in one plane, plane A, is absorbed, and only the light going, say, vertically is allowed through. So we say that it's got a vertical polarization axis. So what we can find, and we're not going to do the maths for it, but we can kind of understand that when you get light, which is just going in all directions, and you make it go through one polarized filter, that means that suddenly you're stopping all the horizontal component. You're only allowing, say, the vertical one, or vice versa, or any angle. Generally, half the energy that was associated with the horizontal movement, will be stopped. Therefore, just intuitively, the intensity will be halved. Okay? The intensity will be halved after the first polarization filter. Now, after the first polarization filter, say that this was your original light. Now, the light after the polarization filter is moving like this. So this is after the first polarization filter. Then you apply a second polarization filter. And the second polarization filter is this orientation here. Sorry. Let's try again without the screen going crazy. So the second polarization filter has got this orientation. Then only you can rewrite this as a component along this axis and a component along this axis, isn't it? You can split this new vertical wave into these two components. Once you apply this polarization filter, this component will be deleted, and only this component will go through. So your new wave, apologize, so your new wave will be this new amplitude. So again, you will decrease the energy again. Now, the formula for that, you can derive it, but we can just use it in this case, is given by this. So the new intensity after the second polarization is the first intensity times cosine squared theta. Theta is the angle between the first one, let me delete this sketch. Theta is the angle between the first filter, i.e. between the light, the polarized light axis, and the new filter. So if the new filter is aligned like this, sorry, I'm not sure why my computer is doing those little random lines. So let me delete them as they come up, because they just make everything confusing. So as if this is your filter, let me redraw it here. Theta is this angle here. This is theta, the angle between the two, between the light oscillation, i.e. the first polarization filter, and the second one, or between the second and the third and the fourth. So if you know this, you can find what's the new intensity down here. Okay, and that means that you can always stop light if the angle between the filters is 90 degrees. And again, you can do this is intuitive. If the light is now oscillating vertically and you put a filter in the opposite direction, there's no horizontal component, you get no light. And you can prove this with the formula. So you've got unpolarized light after the first filter. So the unpolarized light, I've got I0, okay? After the first filter, you get I1, which is I0 divided by 2. So this is I1, okay? After the second filter, you get I, let's call it, which is I1, this, times cosine square theta. If theta is 90 degrees, cosine of 90 is 0, 0 squared is 0, you get no intensity coming through. If, say, instead, let's look at a top example. Again, you've got 0.5 I0 at this point. If the next polarization filter is, say, at 30 degrees, not 90, it's at 30 degrees, then the new intensity is not going to be 0. It's going to be I1 equal to, the new intensity is going to be this 0.5 I0 times cosine squared 30. So it's going to be 0.375 of the original. Okay? The more you rotate the light, the more you keep losing energy, but you can calculate how much using this formula. That also means, by the way, that if you've got two filters like this, say 90 and 0, or 0 and 90, you get no light out. If you rotate the light slowly, if you've got 90, 30, say 0, 30, and then you put another filter here, which is like this, well, now the light hitting this filter is not vertical, it's at this angle here. So you will actually get something through. You can rotate the polarization 90 degrees, you just cannot do it with two filters. You need to do it with multiple stages, okay? Each stage you lose energy, but you can rotate the polarization. There's an example in the tutorial that we'll work with during the tutorial class, okay? So this example is important. Remember, Prof. Dan said important. Please bear it in mind. It probably means it's going to be assessed. Okay? And I've not seen this test. I don't know what this test contains. But if it says important, bear it in mind. So you've got three polarizers. So you've got polarizer 1 and polarizer 2 are fixed. So 1 is, say, vertical, 2 is at 30 degrees. Now, polarizer 3, you can set it. It's got a variable angle to that of P1, okay? For what angle theta do you get the minimum intensity, which means 0, of the emergent light being here? What is that going to give you? What is going to be the 0? Of course, what we want cosine 90 equals 0. So we want this third polarizer to be at 90 degrees, not from P1. P1, at this point, it doesn't matter anymore because the light has been rotated by P2. Now the light goes like P2, not like P1. So you want P3 to be at 90 degrees from P2. And 90 degrees from P2 means 90 plus this 30 degrees here. Or technically 270. So it can be 120 degrees or it be at 300 degrees. Sorry, going on here. Okay, that's because it's the same radical angle. So it's basically saying, if I draw, this is P2, and I draw P3 like this, I can say that it's, this orientation is 300 degrees, or that it is 120 degrees. It's the same orientation, okay? This is 120, this one is 300, okay? Same actual position. Okay, and this is really about it, and this is a more detailed calculation. So P3 will be 90 plus 30, 120 degrees. So now the angle is 90 degrees, which means will give me a 0 intensity. The other solution will be 90 plus 30 plus 180, which again will say cosine square of 270, which is 0 degrees. Okay. Now, a little bit of applications of this. Why are we doing this? Now, we're doing it, first of all, because it's an important general topic. It's a topic that is very, applicable to knowing physics. And the thing is, it is applicable to a lot of situations, more than you actually can think of. First of all, liquid crystal displays, LCDs, okay? They work by applying an electric voltage to a liquid crystal, which orientates the molecules of this liquid crystal and makes it polarizer. That means that if the light is already half polarized, you can stop the light or not. So You can either polarize it in one way or in the other, meaning more light exits or less light exits. Okay, and that for each little crystal you can control whether it's going to be lit or not lit. That means you can stop this. Another thing, I remember traveling on a more modern plane. Well, not necessarily more modern, but it was that model of plane. I think it's a Dreamliner. Is it the 787? Something like that. In that plane, you don't have blinds. You have polarizer on the plane windows. Okay, so instead of closing the blind, you just push a button, and the glass polarizes, so it stops the light. It happens in Singapore as well. I mean, of course, it happens in Singapore, but I mean in the light trail. I traveled in the Choa Chu Kang light trail, and when the train comes near a building, near an HDB, the windows go dark. Basically, they don't want you to look inside the building. Okay, otherwise everyone passing the train could see inside the windows, which is not nice for the people living there. But the way they do it, they can turn it off and on, having polarizers. So probably the glass already polarizes the light one way. Okay, and when you get close to this building and a voltage applies, there's some kind of liquid crystal which turns on and applies a polarization filter at 90 degrees from the first one. And suddenly you cannot see through anymore. Okay. One thing for engineering is photoelasticity. So polymers, a bit like liquid crystals, but in this case not with voltage, if you have transparent polymers, so polymers means basically long chains, rubber is a polymer, okay? They change their polarization properties when they're stressed. Okay, when you apply stress to them, they rotate the light, and they can rotate the plane of polarization slightly. And this is related to the level of stress. So what people can do is they can have a light source, a strong light, apply a polarization filter behind. So behind this sample, there's a polarization filter. Okay, so there's the light source, there's your filter, there's your sample here, there's your machine with the sample. Then you apply a 90-degree filter going this way. If the sample is not stressed, you don't see anything. As the sample is stressed, the light gets rotated a little bit. Okay? And as the light is rotated a little bit, suddenly it can make it through the second filter. Now, this effect is dependent on the wavelength of the light. So this effect becomes stronger or weaker for different light wavelength depending on the stress level, which means that what you actually get is nice light, different colors as the sample is stressed. You basically get a pattern that once you go on in your study and you see FEA, you get a pattern very similar to FEA. And so what you can do is you can use this to map the stress in your material. And you can do a calibration to get different colors for different stresses. And you can kind of then get a nice map where the stresses are. So here, if you've done a little bit of bending, you see the tension and compression stresses of this beam. Here, you get the tensile stresses, okay? You see the change as the stress goes up, as the tensile test progresses. So that's an application of polarization, which we can use in the lab, actually, okay? So, more or less finished. This is quite a small topic. So let's summarize quickly. We looked at the beginning what progressive waves are. Progressive waves are waves that transfer energy along their path. And they can be of two types. Transverse, where the particle moves at 90 degrees from the wave direction. So basically, like water waves, oscillation up and down. Or longitudinal, where the particle moves in the same direction as the wave, not along with the wave, but they just oscillate in the same direction. And an example of this is sound. Now, we found that the wave velocity is f lambda, where lambda is the wavelength and f is the frequency. And we defined then the phase difference between two particles. Each particle in a wave moves as an oscillation, like you did last week, okay? But they move at a different stage in their oscillation. Their phase difference is defined like here. Basically, a function of their distance along the path or their distance in time in terms of the oscillation sequence. We then looked at the intensity, and we said that the intensity of a wave, a spherical wave, is proportional to 1 over r squared. We basically said that because the intensity is proportional to the amplitude square, the amplitude square of the wave is proportional to 1 over the r squared. Okay. We then said that we then looked at polarization, saying that only transverse wave can be polarized. By the way, what is conclusive proof? It's conclusive proof that the EM waves are transverse waves. Why only transverse wave can be polarized? Well, if your wave is in the direction of the motion, how can you polarize it? It's already moving in just one direction. Okay, so there's no way to polarize that. Only transverse waves that move on 90, where the oscillation is 90 degrees from the wave direction, can be aligned. Okay, it only makes sense for those waves. Because EM waves can be polarized, then they mean that they're transverse waves. Okay, and we looked at the intensity, the effect of polarization on the intensity. So after the first filter, the intensity is 0.5 of the original. After any subsequent filter, the intensity becomes I times cosine square theta. I theta being, with theta being the angle between the two filters. Okay, so that's about it. That's all we need to do for this. We'll look a little bit, we'll look at more examples for all of this in the tutorial. So you look at the tutorial with Prof. Tan or with me, okay? And we'll go through some examples where we'll calculate the intensity of different waves and we'll calculate the effect of polarization, okay? Next week, you'll take all of this and you'll actually develop the maths a little bit more, and you look at standing waves, and then you look at some pretty interesting effects that can be observed with EM waves, especially. Okay, so you'll do that with Prof. Venkat next week, and that will be actually the final lecture of this module. So very good, you're almost done. Okay, okay then. So could we have extra practice of all topics for finals? Now, talk with your tutor. I work with the civil engineer students, but I can't, I'm not responsible. I cannot take over the work for my colleagues, for the other students. I give generally extra examples. You can ask your tutor if you can get some extra example. You also have the textbook, okay? So you can go and look at that. My suggestion is also, see if you can get some extra examples from the textbook. For Maru Tengen, I guess you're not in civil engineering, are you? You're probably in EDE. Okay, yeah. So talk with Prof. Tan. Hopefully Prof. Tan will be able to give you some extra practice, okay? But do go through the tutorial sheet. I think in this area, if you can do the tutorial sheet, you'll be more or less okay. Yeah, okay. So I think it's... something that Prof. Tan will decide. Somebody's asking me about the formula sheet. Prof. Tan will decide. It's up to him. At the moment, he prefers to put few formulae about this and then to ask relatively more straightforward questions. So it's a balance. I can put all the formulae and then ask you very advanced questions. Or I can put fewer formulae and then you have to remember a few basic formulae, not that much. You have to remember maybe, I don't remember what's in the formula sheet, but maybe things like this, things like this formula here. Maybe for oscillation, you need to remember the x0 sine omega t, okay? Or x0 cosine omega t. That's it. But if you remember those, then you can do the questions. So it's a balance, but I'm afraid it's up to Prof. Tan, okay, to decide what's going to be on the formula sheet for this area, for these topics. Okay, so if there's no more questions, we can conclude for now, and we can all go for a slightly earlier lunch than planned. So so I'll see some of you on Friday, the civil engineering students. For the EDE students, probably I'm not gonna teach anymore. This was already unplanned, but good luck with the rest of the modules, this module and the other ones. And yeah, maybe we'll see each other again at some point in the future. So good luck for everything. And I'll stop the sharing. I'll see you on Friday for the civil engineers. Bye bye all.